All right. So in this next section, this is part of the pre-post sim kind of art direction section of the lesson. We're going to be talking about uh, follow curve, and we'll talk about briefly about the path tool that uh, exists up here on the shelf. But we're mostly going to be talking about creating our own custom tool. Um, and the idea is here is to get you guys comfortable with making kind of very specific custom tools that do exactly what you want. And this is going to be revolving around Vex. There's going to be a lot of Vex in this. Um, yeah. So I'm going to attempt to, as this is going to be a bit on the long side, there's lots of parts to it, and I want to kind of walk you through the process. Um, it's going to be on the longer side, so I'm going to try and split it up into kind of small, discrete portions. If you like are feeling fairly comfortable and you feel pretty comfortable with Vex already, you can just come and take a look at this operator that I've created and read through the code yourself and kind of get you know decipher it on your own account. But if you look at this and kind of are intimidated, follow along with the video, and hopefully I'll be able to clarify. It'll help clarify some things. So, but let's start at the beginning here. So I have three kind of dot networks here. The first one is a dot net that I've set up, and I've created a curve, right, which is what this is. Nothing fancy here, just a curve, and I've used a ray sop to, so I've drawn the curve, right, and then I've used a ray sop to project it onto the ground here. So nothing too specific. Yeah, and then let's see. Yeah, so in this example here, it's plain old crowd sim, very similar to what you've seen already if you've gone through the locomotion section. But you'll notice there's this pop steer path tool, and this is basically what gets created when you click on the path tool. It inserts this into your DOP network. And you can see it's looking at the path. It's got a number of different settings associated with it. Yeah. And yeah. So this is kind of the the tool that as it exists. So, and if we play forward, this is kind of the behavior we're looking at. I'm going to change the background to dark just so you can see it a bit better. So, yeah. So these guys move along. They're being influenced by the path, certainly. Okay. So, this is the path tool. Perfectly fine. It does what it's designed to do. But say you want a different type of behavior. Say you want a kind of more, customized behavior. This is something you can get. All you have to do is think about what kind of behavior you want, and then come up with some logic to get you there, and then implement it with some Vex, and you're off to the races. So to kind of illustrate that you can do this in like the most basic form, but basically, in this example, I've just created a geometry wrangle. It would actually be more appropriate if I use a pop wrangle for this rather than a geometry wrangle. But this is what I made it, and for this example, it's not the end of the world. But when you're doing it, a pop wrangle is probably the better way to go. And a pop wrangle is a wrangle that's specific for manipulating particle systems. A geometry wrangle is more generic, and it's meant to kind of alter any type of geometry you have, not necessarily particle specific. Okay, so here all I've done is I've created a steer force, or I've altered the steer force attribute. If we take a look at our agents and we come down to geometry, hide all attributes, we can find steer force and steer weight. And for like altering the kind of trajectory of a agent, these are the things you kind of want to look at. Steer force, kind of controls direction and magnitude, and then steer weight is if you're combining multiple, have multiple operators that you're using to combine steer forces, the weighting is used to kind of compute how much each of the different steer forces should contribute to the overall speed of the agents. So all I've done here is said, hey, move in this direction. So it's like, positive X and positive Z. And I've set the steer weight to some value. And you can see what it does. These guys are basically running in a diagonal line as you'd expect. Okay. So that's fantastic, but nothing too special. The thing that we need to take away here is this is, if we're going to make our own kind of curve tool, ultimately the goal is to manipulate these two values. And as long as we can figure out an intelligent way to manipulate these two values, we'll be in good shape. So let's come back and take a look at this tool that I created here. Just give it a moment to cook. So this is this tool that I made, and it's got some controls on it, which I'll briefly explain to you. So it does two things. Let's first take a look at what the sim actually does. So you have these agents, and the agents start off maybe kind of a little ways away. And there's essentially two forces at work here. One is called the tangent force, which is the direction along the curve. And the other force is called the dir to curve, which is basically the direction to the curve, or the closest point on this curve. So what these agents are doing is they're, in essence, two things working on them. One is a force that's pushing them towards the curve if they get too far away. And then another force that's pushing them along the curve. And this, for this example, is kind of giving me the desired effect that I want, right? Which is you have these agents and they're kind of walking on a specific path, and they're, kind of staying within a kind of certain boundary within that path. And I'm controlling that boundary with this ramp that's kind of controlling fall off. And this there's also a kind of effective range where these guys will work, right? So the minimum distance is 2, and then the maximum distance is 5, and then same thing over here. Okay, so this is kind of the introduction, and from here I'm going to, I'll see in the next video where we will start digging into writing this Vex code. Okay, see you in the next one. All right, so we're going to be taking a look at going through the specifics of kind of writing this code. There are a few, one of the things about writing tools for DOPS, specifically like Vex, is, and this is just kind of a tip, when I wrote this, I just dropped down a Wrangle and started typing. But I've been using Vex for a very long time, since it first came out in version 4 of Houdini. One of the things that I find really useful when prototyping a tool is to particularly if it uses Vex, is to prototype it in the SOP context. Number of reasons for that. The first being that it's, the SOP context is something that you're probably very familiar with, it's very intuitive, and you don't have to consider simulation. The other thing is that you can have your tool really work in isolation without having to worry about all these other nodes and what they're doing. Because remember, one of the things about DOPS and how it works is it's kind of like taking all of these nodes that have a bunch of instructions and then assembling those instructions together and then using that to do the processing. SOPs, doesn't work in that way. It just, says, okay, give me my geometry and run some sort of process on it. So it's a much more kind of direct way of working, and it can help you debug and find problems much easier. So that's what we're going to do here in this video. So I'm going to just create a node, and I'll call it Vex test. I'll color it orange just so it jumps out at us. And I'm going to go in here. And for the purposes of this test, I'm going to just use a sphere in place of one of my agents. A sphere is, in essence, just represented by a single point. We can turn on the display of that. And you just see it's a single point. So, an agent is also represented by a single point. So this is kind of like a good thing to test with, and it keeps things simple. Right now I have, I'm ghosting other objects. So I'm going to hide those other objects. And I'll drop down an object merge and go grab my curve. So bam, curve object, out curve. Great. And then I'm going to drop down a wrangle, and I'm going to input this sphere, which will double as our agent, into the first input, and then the curve into the second. So this is kind of what we're looking at. And just a little bit of note here, with SOPs, obviously it's really obvious where your input is and what it's doing. In DOPS, when you're using a wrangle, there's an input tab over here where you get to specify your inputs. So the first input is, myself, which means the incoming geometry to this DOP. The second input is a SOP, and it's pointing over here at this SOP geometry node that I created that's doing some extra processing of the curve. So I'm just going to, click over here and look inside. And we have this little network that's doing a bunch of stuff. And we'll need this to do our kind of little Vex example. I'm just going to copy it and bring it back over here to the object level. And we can dive inside here, and I'll just paste it. And as a matter of fact, these two object merges look at the same place. So, wow, no, I'll just, I don't need these switches. I don't think they're doing anything useful anyways. And I'll connect the polyframe here. And I'll kick the output of this wrangle. This is what we're actually using. Oh, whoops. So let's see what we got. Okay, so the first thing that we're doing here is we're on the curve anyways, is we got this polyframe and we're making a tangent. We're calling it normal. This just makes it really easy to visualize because we have this default visualizer for normal over here. So everything, we see that it's working, everything's grand, but it's pointing in the wrong direction. So I do a couple of things. The first thing is I take the normal and I normalize it. When you normalize a normal or a vector of any sort, basically what you're saying is make the length of the vector 1 unit. This is useful because if the length of your vector is 1, and you want to scale that vector by 2, you just go 2 times your normalized vector, and you know that the length of the product will be 2. This is very handy for things like velocity, right? You can normalize your velocity so it has a length of 1, and then if you want your goal velocity, you want it to be 10, or your goal speed rather, you want it to be 10. You just multiply that normalized velocity by 10, and you'll know that the vector that's created will have a length of 10. So that's what normalize is useful for. The other thing I'm doing here is I'm stuffing it into a velocity vector. Because ultimately that's what we're going to use it for. And I've just negated it, and I've negated the normal as well for display. So by negating, I mean switching directions. So we're in good shape. Yeah. Okay, so let's see. Incidentally, maybe not, the cleanest code. I could have probably just done a polyframe, put it directly into velocity rather than normal, and then I would have an extra attribute. But for the purpose of this and the purposes of visualization, it's perfectly fine. Okay, so the next thing we need to do is we want to query some information from this curve. Namely, we want to query information at the closest point on this curve. And we want to know two things, right? We want to know the velocity, so I can get a direction, I can know which way the agent is supposed to go, and we also want to get the position. And if we have the position on the curve, the closest point on the curve, then it's very easy to kind of make a direction vector between the agent and the curve. And the reason why we want to do that is we want to kind of have two forces, right? One pushing along the curve, and then one pushing to the curve, or making the agent come closer to the curve. So let's kind of work on a way to do that. So the first thing I'm going to do is I'm going to use a function called xyz dist. So let's go take a look at that in the documents. So great. I'm going to go to support, documentation. You can do this with the help browser, but I find it's faster to just do it off the web page. So I'm going to go xyz dist, search. There's a vex function. Okay, groovy. You'll see that there's a number of different ways you can use this. The argument list for the function, there's different ways you can run it. So you can run it with 2 arguments, you can run it with 4, 5, etc. Just so you know, this is called an overloaded function, which means it basically has different kind of sets of arguments, and an overloaded function can also return different types. In this case, it's all returning floats. But what we're interested in is this right here. And this does a couple of things. So the first argument is the geometry you want to test against. So we want to find the distance to whatever geometry we specify here. In this case, it's going to be this curve, right? The next thing is we specify the position that we want to test against, right? We want to get the closest point on this geometry from this position. And this will be the position of our agent, or our sphere in this case. Then we have 2 extra arguments. These one's called Prim and one's called UV. And I'm going to create these. These are variables that I'm going to pass to this function. So I'm going to create them before I run the function. And what these little ampersands mean here is it means pass by reference, which is a kind of technical programming term. And what it means is I can pass a variable to this function, and the function will assign a value to that variable. So it's going to assign a value to primitive, and it'll assign a value to UV. And so this is handy because a function can inherently only return one value, but by using this, it can return 2 other values, right? So what does like Prim and UV represent, though? Like what kind of value is this function going to give me? Well, what it's going to give me is going to give me the primitive number on this geometry, so the curve geometry, of the closest primitive. So, and then it's going to give me the UV value that corresponds to the closest point on that primitive. And just, kind of bear with me. So the UV value here is not a UV value like a texture UV value that you create. What this is referring to is the kind of implicit UV value on the geometry. So all geometry has an implicit UV set of UVs that they don't exist there, but you can query a piece of geometry and it will be computed for you. So for example, a curve, right? It has a UV value can be computed on that by going, okay, this is the first point, this is the last point, and there's an implied kind of UV space that goes with that. That's what this means. It doesn't mean like a UV texture attribute that you create. It's a subtle but important distinction. Okay, so let's go ahead and make this work. So XYZ dist, I want to get the curve, which is the second input on this wrangle, which corresponds to 1 because it's index 0, 1, 2, 3. And then I want to, we need to have the origin, which is what do you want to measure the distance from? So this is going to be the position of our sphere, or, our agent. Then we're going to pass it a variable called prim and another variable called UV, which we have yet to define. And we're going to do that right now. So I'm going to go, let's see, int prim. I will set it to 0, and I will go vector UV, and I will set that to 0 as well. Okay, and I'm going to make an attribute here called dist, and this is what the function returns. So I just made this into an attribute. We could come up here and take a look, and you can see this attribute, and it says it's 5.9 units away. Now, let's see, 1, 2, 3, 4. Yeah, it seems about right. Okay, so we don't need this attribute because we're going to be doing all the work in this wrangle. There's no need to pass it on to another node. So I'm just going to make this into a temporary variable called dist. And just for consistency, I'm going to come back to this example and see what I named the attribute, the variable here. So I'm going to try and keep it consistent. So target primnum, target UV, distance to target. Okay, so I'm going to be bouncing back and forth between what I've done in Vex or what I've done here in DOPS and what I've done in Vex. So in order to do that or help facilitate that, I'm going to create a quick mark. So Control 1 over here, and I'll back up and go to over here, and I'll go Control 2. And now I can switch back between these guys very quickly and just make sure that things are okay, or that at least the naming conventions are consistent. So I'm going to change this to target prim and target UV, and I'll name this to target, if I can spell, dist. Okay, and then I need to rename these guys as well. So target prim, target UV. Okay, so we're off to the races. And we get error. Typo over here. Groovy. Okay, so we've now got the distance to the closest point on this primitive. We should also have the primitive number of this curve and the UV value for that prim. Okay, so the next thing is how can we use this primitive number and the UV value to get useful information. Namely, we want the actual position in world space on this curve, and we want the velocity value along this curve. So the function we want to use for that is called Prim UV. So there we go, vex function Prim UV. Groovy. Okay, so this function specifies the position using intrinsic primitive UVs. This is what I was referring to before. To use UV stored in the UV attribute. Okay, yeah. What this basically means is it means I'm going to provide it with a piece of geometry, an attribute. I want to query on that geometry. So in this case, the geometry is a curve. And I want to query the position and the velocity. I'm going to do it as two separate calls. And one of the things it needs is it needs the primitive number and the UV value on that primitive in order to query those attribute values. So yeah, let's go ahead and do this. So let's go Prim UV. I'm sampling the curve. I want the position. That's the attribute I want. And I need to specify the primitive. And I need to specify the UV. Groovy. Okay, and then I need to assign it to something. I'll go back to here just to see what I'm referring. Target pause, or target position. So come back to 2, sorry. We'll call this target pause. And I need to give it a type. So vector. Okay, so we now have this temporary variable called target position, and it's vector. It's difficult to visualize what this is because there's nothing to visualize. All these values are getting stuffed into temporary variables. But it's handy to do things like this. So, and I'll target pause. And so what I'm doing is taking the target position and assigning it to the position of this agent. So now you see it snaps to the closest point on the curve. Right? So basically, this is the original position over here, and it moves it to this kind of closest position on this curve. Okay, and just to verify this is doing what we expect it to do, we can move our sphere or agent upstream and see what is happening downstream. So very handy. Yeah, so this is an incredibly powerful workflow. XYZ dist and Prim UV, it's something you use all the time, and it's very, very handy. Okay, so we want to do the same thing, but we want to query the velocity. So I'm going to come over here and change this to velocity. And I will call this target. I believe I used tangent. And so let's take a look, just make sure I did that correct. Target tangent. Okay, in this case, I'm actually sampling the normal, not the velocity. So let's go back to, we'll change this to normal, just so it's consistent. And great. Okay. All right. So let's take a look at this tangent value and see if it's doing what we expect. So I'm just going to make a normal attribute, assign it target tangent, and we should use that, be able to use that to visualize. And I can't see it because I think the sphere is in the way, so I'm just going to drop down and add and delete the geometry and keep the point. And there we go. So there's our direction. So, and this is, this is the direction at the closest point on this curve. So if once again, if I take this sphere and move it, you can see that direction vector is changing, right? Depending on what the closest point is. And I can, move it this way, and you can see that it's, it's finding the closest point, which is somewhere over here, and the directions change it. Okay, so I think this is a pretty good place to stop and for this video, and I'll see you in the next one where we'll kind of continue from here. Okay, picking up from the last video, we'll talk a little bit about this. So we have this, target tangent, which is basically queried this this vector from the curve, and and is using that to kind of set the normal. One thing we want to do is first I'm going to change the display settings on this normal to see what it is actually showing us. So visualize, guides, scale normal. So in my case it's 3.8. I'm going to set it back to 1 so it kind of actually reflects the length. So this, if you look at it, you can kind of see that the length of this normal is already, probably 1 or very, very close to 1. And this makes sense because, I'm guessing polyframe kind of returns a normal value or a normalized normal. But the thing is if you're making a tool, you can't really count on it returning or the input being normalized. So we can, adjust for this, just do a little due diligence and set that equal to normalize. And there we go. So it's now normalized for sure. So, which basically means it's has a length of 1, which means we can scale it by a scalar value, and it'll, it's a way of ensuring that the speed or the force is scaled by a particular amount or equals a particular amount. So, okay, that's great. Yeah, and just to kind of emphasize this, if I, now that this is normalized, I can multiply this by 2. Whoops. And you can see the length is roughly 2 now, right? So that's basically the significance of normalizing a vector. All right, so I'm going to, now that we have this vector, there's a couple of things that I want to do to it. I want to scale it, right? But how much do I want to scale it by, and under what circumstances? So the first thing I'd like is I'd just like a kind of global control to scale this vector. And I'm going to flip back to my .NET here. And I've created this here. I'm just going to copy it so it's the same name. And I'm doing things a little out of order, just in case you're wondering why I haven't, I've done some things but not the other things. I'll get back to that in a moment. So, okay, so basically I'm making a temporary variable called tangent scale, and I'm setting it to a particular channel. That channel doesn't exist yet, so I'm going to click on this little button, which will make the channel for me. And there we go. So I'm just going to scale tangent scale. I'll scale this tangent value by this multiplier that I made. So now I have this parameter, and I can kind of control its scale. And this is just a nice kind of global control to have on the whole thing. Okay, so the next thing I want to have is I want to have another scale. And this scale, I want it to be affected by the distance away from the curve. So I want, in this case, I want this tangent force to be stronger the closer it gets from the curve, the closer it gets to the curve, and I want it to be less the further away it gets from the curve. So yeah, let's let's go ahead and do this. The first thing I need to do is I need to kind of, in order, I want to use a ramp to kind of control the fall off away from the curve. And a ramp basically takes a value between 0 and 1. So what I want to do is establish kind of like a min and max distance and remap that min and max distance to 0 and 1 so that the ramp that I create kind of covers this specific area or range that I want to work with. So yeah, let's do that. Fairly easy to do. I'm going to just jump back to my other code, make sure that I get the same names. So yeah. Okay, so tangent fall off is what I call it. Okay. And yeah, we'll go back. Oh, whoops. A little typo there. All right, so yeah, so we have tangent scale. That's great. And I can put a little note global. Remap ramp arm. All right, and so I'm going to take this, and so I need to know the, I need to feed this the distance that this point is away from our curve. And if you remember, we got this with the XYZ dist, it returns this target distance. So I'm just going to go target distance, and let's see. I'm going to refer to a parameter because I want to have user control. So I'm going to call this tan min, which will be the minimum distance, and ch tan max, which will be the maximum distance. And I'll close that up and remap between 0 and 1. And there we go. Okay, and once again, I don't have, these parameters haven't been created yet, so I'm going to click this button. It creates it automatically for us. And then I can establish like minimum and, I don't know, maximum distance of 1 of 4. Okay, so this is great, but it'd be nice if we could kind of preview or get a sense, you know, let's just examine this tangent fall off. So I'm going to make an attribute and call it test. Set it equal to tangent fall off. And there we go. And then we can just kind of look at this geometry in the spreadsheet. So you can see it's 0.8. So it's kind of in the upper boundary of this range. So it's, you know, not quite 4 units away, but pretty close to it. I can bring this, bring this down to say maybe 3. You'll see that, you know, oh, yep, it's, you know, outside of this range. It's more than 3 units away. So it hits the maximum, which is 1. So I'll just set that back to, say, 4 for the time being. And similarly, if I, you know, start moving this sphere in, and if we could take a look at the geometry spreadsheet, and we have to have the other node selected. You see a test is approaching 0. And if I get it close enough, it'll actually be 0. See? Okay, so great. We now have this kind of value that goes between 0 and 1, depending on how close this agent is to, just undo this, put it back, how close it is to the curve. So yeah, great, fantastic. I'm going to bypass this. We don't need that. And actually, I'll just blow it away. No sense muddling things anymore. And then I'm going to use a ramp parameter. So let me go back to my DOP and just check what I named things. Okay, so tangent fall off. Okay, so, all right. I suppose I could have just copied the whole thing, but all right. So let's click on this button, and there we go. So groovy. So tangent fall off. We have what I'm doing is instead of making a new variable, I'm just assigning this value or reassigning this value. So I have this tangent fall off. It now goes between 0 and 1. And I'm using that 0, 1 to look into this ramp curve. And then depending on wherever its position is in this kind of normalized space between 0 and 1, it'll return a value on this ramp. Yeah, so this is in essence what it does, and it will give me a float value. I'm going to change this curve because the closer it gets to the curve, the stronger I want the force to be. So just set that to 1. And likewise here, the further it gets, I want it to be 0. And then I will multiply this by times groovy. So we now have tangent scale, which is acting as like a global scale. And then we have the tangent fall off, which is basically being controlled by this min and max value as to determining the range. And then that's in turn being fed into this ramp, which is returning the value of this ramp. And you can change it to like Bezier or whatever you like. Add some more keyframes, and you're off to the races. Yeah, so you can see now that this vector is much smaller than it was before. If I, just to double check that, I can do like this, and that's how it is with the tangent scale. The tangent scale is currently 1. So if we incorporate the ramp, you see that it's, oh, what did I do? Gotta get rid of that semicolon. You can see that it's much, much smaller. Now, if we grab this sphere and take it and drag it closer to the center and display what we have, we can see that this is much bigger now. As a matter of fact, what I'll do is I'll just, in order to kind of illustrate this a little better, I'm just going to do, or actually, take this plus sign $$F. Actually, I'll use a new syntax frame. And let's see what we got. So now it should be animated, so it should be getting closer and farther. And I'll just increase the amplitude a little bit here. So this is just a kind of nice, easy way to see motion close to and away. So as it gets closer to the curve, it gets bigger. As it goes farther away, it gets smaller. And you'll see at a certain point, it no longer gets bigger, right? It stops getting bigger. That's because it's in 1 unit. It's this minimum threshold that we've kind of set. So if I were to set this to 0, then it would be waiting until it would keep getting larger right up until the point it hits the curve, right? That's as big as it gets, and then it kind of goes back down. So by setting this to 1, we now have this effect, so where it kind of reaches its lower threshold. Okay, great. So, and this, of course, is, as I mentioned, like if I move along the curve, this tangent is going to follow the curve. So we're in good shape. And we can use this, to control the force, right? So the closer it is to the curve, the stronger we want the force to be. The further away, the less force we want. All right, so great. That's that part done. So this is all the the tangent section, we can call it. The other force we want, right, is we want a force that's pushing into the curve. So we want one force that's following the curve, and we want another one that's pushing us towards the curve, or pushing our agent towards the curve. And I will be back in the next video to discuss how we do that. Okay, see you in a minute. Okay, we're back. In the previous video, we talked about basically finding the tangent from the curve and scaling it by a kind of master tangent scale, and then another scale that was based on distance, and that distance would be remapped to 0 to 1, and then fed to this ramp, and that would give us an additional scale value for this direction. Okay, so that's working well. The next thing we want to do is we want to do the same thing, but for the vector, a direction vector that's pointing to the curve. So the idea here is we want, one force is pushing along the curve and the other one is pushing into the curve. All right, so let's go about putting that together. I'm gonna swing back here to my. Forgive me. I'm gonna swing back here to my wrangle and take a look at what I've done here. Yeah, so I have another scale here called, well, actually, first thing I want to do is direction to target. I'm just going to copy this so that I make sure I have the names correct. All right. So, hold on a sec, just redo my quick mark here. Okay, so I'll put this down here. Oh, did not paste it properly. There we go. Okay, so what we queried the tangent, and that target tangent, we normalized it. But then there's one of the other things we queried was the position of the closest point on the curve, and what we want to do is basically find the direction from our agent to the closest point on the curve, and compute that. And I'll just comment this out for a second so you can see what we're doing. So we basically want to find that closest point and then compute the direction to that closest point. Okay, so yeah, let's go ahead and do that. So the direction is going to be called direction to target, and what I'm going to do is I have the target position, so I have the point on the curve, and I have the position of the agent itself, which is represented by at P, the position attribute. And what I can do very simply to get this value is just subtract the position of the agent from the target position, or the position on the curve, and we should be in business. So I'm going to come back down here and comment out this line because I want to visualize this with the vector we just created. So to target. And let's take a look at that. There we go. Okay, so this is as you can see, it's pointing from the agent to the curve. And as the agent goes away, yeah, it scales, right? So because this is a kind of one of these really useful comments or things to keep in mind in terms of working with vectors and stuff like that. If you take the position of one point and the position of another point and subtract one from the other, what you get is a direction to that point. The argument over here, or the position on the right hand side of the subtraction sign, is basically going to be your origin, right? So where you're starting from, and the target position, or the position on the other side of the left-hand side of the subtraction sign, is going to be what you want to point to. So yeah. Anyways, so we have this vector, and you can see as as the point moves, it gets longer and smaller, right? But we want to scale this, and we're interested in the direction to the curve. We're not really interested in the magnitude or how long this is. So what we're going to do is we're going to normalize this. So to make it unit length of 1. Great. And there we go. And now you can see that it doesn't change length. It just changes direction depending on where it's pointing. Okay, so that's good. What do we need next? Well, we need a global scale for this direction to target. So I'm going to flip back to my other, and what did I call it? This is what I called it. I'll copy that. Come back here, and there's nothing fancy here. I'm not doing, there's no magic or anything like that. I'm just copying it to make sure that my naming convention is the same and that I've named everything similarly. Yeah, so now we have another kind of global scale that's going to work on this vector. So I'm basically taking these two vectors, one for the tangent and one for direction of the curve, and I'm going to combine them at the end. At the moment, I'm just working with this direction to target in isolation, so we can kind of appreciate what it does, and then we can combine everything at the end. Okay, so that's great. Let's create a parameter so we can get this working. All right, so it creates this parameter here, and I'll set it to 1. At the moment, it's not doing anything, but I'd like to talk a little bit about UI here. So here we have a bunch of parameters that are all dealing with like the tangent, control of the tangent, and then we have this control, which is dealing with direction to target, right? Or direction to the curve. It'd be useful if we could have some convenient way of separating these two. So what I'm going to do is I'm going to come up here, and on this node there's this option for edit parameter interface, and I'm going to create a folder, and I'm just going to drop this folder into this code tab, put it at the very bottom. Yeah, go, just switch that. And I'll grab all of this stuff and drop it into this folder, and I'll name the folder tangent. Apply. So let's take a look at what we got. So we now have this folder called tangent, and the parameters related to that are in here. I'm going to do the same thing. but I'm going to do a separate folder. I'll call it dir to curve. Hit accept. And now we have another one. Oh, and I forgot to actually drag my parameter in there. That would be useful. Great. And I'm going to swap these guys around because I think for whatever reason I like that better. Okay. So we have the kind of global scale. And the next thing that we need is similar to what we did here, right? We're going to do, we're going to remap the distance for a ramp parameter. So we're going to kind of choose a min and max distance, and we're going to remap that to 0 to 1 so we can feed it into a ramp parameter. So I'm going to switch back to my wrangle here, and I'm going to just grab this just so the name's correct. And where are we here? And let's see, we're going to use target dist again, right? Because this is the distance to the curve. Just a reminder, typo. This is what we got from the XYZ distance function, which gives us the distance to the curve. That's what it returns. So I'm going to do that, and I'm going to ch the distance to curve min, ch distance distance to curve max, and remap it between 0 and 1. Great. So that's done. And let's see. Go back to our other example and get the name of this ramp properly. I'll get the names. Make sure those are correct. So this is, fairly straightforward, just creating a ramp. Nothing fancy. And let me Control Z for a minute. There we go. Okay. Sorry, little typo. Max. There we go. And just paste this again. And it's called dir to curve fall off. Great. So that's done. We have an error. I need to create these parameters, I suppose. Oh, I forgot a brace. Okay, I'll create these parameters. So I now have my min and max and the ramp. I'm going to edit the parameter interface and drop it into this folder. Grab those, drop it in here, and hit accept. I'll set this to 1 to 4, just for the hell of it, and great. So I think we're in good shape. And what we can do now is we can test this. So I'll go v at n, similar to what we did further up here, and it's called dir to target, which is the direction, the vector, right, times, and to target scale times dir to curve Yep, great. All right, now let's see what we got. Oh, let's take a look at this parameter first of all. Yeah, so, okay, so as it gets further away from the curve, right, it gets stronger, which is kind of what we want, right? We want it to be, we want the agent, if the agent drifts too far away from the curve, we want him to be pushed back to the curve. So this is kind of doing what I want. But I'm going to change this ramp a little bit just so it's a little bit, maybe reflects what I want a little bit more. So I'm going to set the min to 0, so it's right on the, curve. That's going to be the kind of range. And then I'm going to set a keyframe here and drop it down to kind of 0. I'll have another one like this perhaps. And then do something like this. So let's just kind of take a look at what this does. Okay, so and just so we can see this a little bit better, I'm going to increase the magnitude to maybe 5. So perfect. All right, so the idea here is as the within a certain range, so there's a kind of middle section here. There's going to the force that pushes this agent back to the curve will be quite strong. But eventually, if it gets far enough away from the curve, it will no longer have any influence. Right? And when it comes closer to the curve, there'll be this region where it'll be really, really strong. But then when it gets within 1 unit, or when it gets inside of this kind of area right here, it'll fall off and it'll go to 0. And the idea here is that once the agents are within a certain range of this curve, I don't want them to be pushed towards the curve anymore. I just want them to get close enough to it. And then once it's close enough to the curve, the other force, the tangent force, can kind of take over. So this is the kind of design that I'm kind of going for here. Of course, you have this ramp parameter, and you as a user or an artist can change this to do whatever you think is suitable. But this was kind of like my logic behind setting this up. So, great. Okay, so that is basically the direction to kind of target, or direction to curve. And that's the end of this video. In the next one, we're going to talk about combining these two and then bringing it into DOPS and getting it all to work together. So I'll see you in the next one. Okay, so yeah, in the last video, we basically added this kind of direction to curve force. And we previously computed this kind of direction to tangent force, which is in this commented line. So now we're going to get them working together. Okay, grab this, copy, go over here, hit plus, because I'm going to add them together. I just want to make sure I have a semicolon at the end there. Good. All right, and we can delete this line. Let's see what we have. So you see now we have this kind of combination of the this kind of direction to curve vector as well as the tangent vector, and we're adding them together so they kind of create this force. And this is the result of it when we sum it together. Now that we have this working, let's come in here. We're going to grab all this code, just copy it. And we have a test case now, right, that works inside of SOPs. Now we can go over to DOPS and escape. Just going to stop this from cooking. Go back to first frame. Turn off the normal display, and I'm going to take this wrangle and remove it from the chain. Just do that completely so there's no confusion. I'm going to drop down a pop wrangle. Great, and I'll copy the code. First thing to be aware of here is that I've copied the code, but I no longer have any of the parameters. So let's just go ahead and make those. So now we have our parameters. Great. I'm going to take a minute, edit the interface, just so we can have those two folders and it's a little bit clearer what's going on. Groovy folder. I'll drop this into code. Drop it to the bottom here. Oops, whoops. And I will call this tangent. And I'll grab another folder and drop it in here. Drop this above. Drop the tangent above this one. Good. Rename this to dir to curve, direction to curve. And then I'm going to put the appropriate parameters in the appropriate folders. Direction to target, tan min, tan max. Both of these go in here. Tangent fall off goes in here. Looks good. These three guys I'm going to put in here, and we should be good to go. Hit accept. You can drive down here, and fair enough. There's our parameters. They're defaulting to 0, so not terribly useful. So let's put something in here. 1, and then I don't know. Let's see, 1 and 4, 1 and 5. These are just distances to the curve. Yeah, so tangent fall off, I want the tangent to be stronger, right, as it gets closer to the curve. So like that. In direction to curve, I kind of want it to get, as we get away from the curve, I want it to be stronger, and as it gets closer to the curve, I want it to be, well, as it gets closer to the curve, I want it to fall off, and as it gets further away from the curve, I want it to get stronger, and then as it gets even further, I want it to fall off again. So that's what these kind of things represent. And let's go start curve and take a look at what we're doing, and play forward, and let's see what we get. And nothing happens. And the reason why nothing happens is because we've created this pop wrangle, but we failed to establish inputs. So first inputs, I'm just using myself, which basically means the node's current data, and SOP for the second input, and I'm going to point it over here to this curve sample example, or little network that I made. And remember, this is adding the tangent to the curve. Yeah. So let's go back up here and we'll point ourselves there. So inside of the dot network, it's called curve sample out. And let's see if this works any better. Scroll down, take a look at. Interesting. Still not working. Maybe it needs to be recached. Let's see. I'll reset the sim. Come back down here and let's take a look. No, still not working. All right. So what am I missing? Well, this is pretty clear. What I'm missing is I'm trying to set the normal on these agents, which isn't going to do anything in terms of direction. I need to alter steer force, the steer force attribute, steer force, and I need to have a steer weight to go along with that. And let's see if this works now. There we go. All right, so we got something working now. So you have these agents that are kind of in range. And so these agents that kind of fall within this threshold area. So that's halfway somewhere between 1 and 5 units. So that's what, 4 units. So somewhere around 3 is going to be this kind of midpoint, right? Those agents will be attracted to this curve, and the ones that are outside it are not going to be attracted, right? So they kind of just keep running, which makes sense. That's what this tool is meant to do. And then you can see that these agents are now, running along the curve and conforming to it, and staying within this kind of threshold area that we've established by DC min. So it should be 1 unit on either side, roughly. And that's kind of what it looks like, right? So if we kind of wanted to bring these agents back over, what we can do, let's see. Change this to 7 maybe. And now everybody starts kind of falling in line and getting, attracted to the curve and following it. Yeah, so our tool is working and we're in good shape. This took a while to put together, but it's actually a pretty basic tool. These can get a lot more intricate and a lot more specific. There's an entire multitude of things that you can do with Vex in terms of controlling behavior. And we have, at our fingertips, or in terms of what we can access, all of these functions. And I'll just go to the Houdini docs game. So type in Vex functions. So yeah, so there are a lot of different Vex functions that can do a whole bunch of different things. This is just giving you a little taste of what you can do, and something very basic to kind of control the direction that somebody moves or an agent moves. So yeah, I hope this was informative, and I will save this file out for you guys, and I will see you in the next video.